Alright, so this is one of this is probably my favorite part about this chapter of biochemistry, um, which is the Van Hoff equation. The Van Hoff equation is a pretty simple to derive, easy to understand equation, and I hope you'll agree with me after this video. And we use it to look at how thermodynamics and the equilibrium constant, so kinetics and thermodynamics, interplay. Now, if you look on the left of the screen, what we have at the top is the Van Hoff equation. The Van Hoff equation is right here, VH equation. And what it states is that the ln of the equilibrium constant is equal to the delta H standard over RT plus delta S standard over R. Now, this might not look super familiar or useful at first, but let's write it out and let's try to dig into it and see what's so useful about this form. So I write it again, ln K is equal to, I hope you can see that I can break up this term here into negative delta H standard over R, and let's look at that as a term on its own, times 1 over T plus delta S standard over R. So the question is, what makes this equation so useful? Why are the graphs produced by the Van Hoff equation so readable? And the answer lies in the form of this. Now, many of us haven't taken algebra in years, but hopefully most of us can remember this equation. Y is equal to mx plus b, where m is the slope, x and y are the variables. This is the independent variable, so this changes, and this depends on the change. This is the dependent variable, and b is the y-intercept. What does that have to do with this equation? Well, let's label the Van Hoff equation in its components. Let's call this y. Let's call this, now m has to be a constant. Is this a constant? Well, we know that R is the ideal gas constant. It is by definition a constant. And delta H standard for a given reaction does not change. So again, we are changing the temperature, and K is going to change as a result. The equilibrium constant is going to change as a result. And the delta G non-standard is going to change. And there's another equation that relates that, as you know from the previous question. But the standard enthalpy, entropy, and free energy do not vary. So this is indeed a constant. This is m. It is a constant. 1 over T changes as temperature changes, so this is the variable. This is x. And finally, delta S standard over R, as we just identified, this part is a constant, and this is going to be equal to b. So we do have a y equals mx plus b style equation from the Van Hoff equation. And if we look at this graph here, you'll see that ln k is the y-axis, as we would expect, and 1 over t, this is scaled, but 1 over t is the x-axis. So indeed, we're looking at a linear equation, and we can look at various components of it, and we can determine, because r is a constant, we can look at what is delta H, what is delta S standard. We can use 1 over T and zoom in and find out what is ln K at a certain temperature using this equation. So it has a lot of uses. The other thing you want to understand about the Van Hoff equation is, where does it come from? I told you it's pretty easy to derive, and I think when you have low-hanging fruit like that, it can be very beneficial to just go ahead and derive it. And so let's do that. Now, what we're looking for, the final form that we're looking for, as we just discussed, is the form where we have ln k is equal to delta h, negative delta h over r. I'm sorry, my cursor is not big enough on this episode. My bad. Delta h over r plus, and standard, plus delta s standard over r. And we're going to start with two equations. Delta g standard equals negative rt ln k. And we also know that delta g standard is equal to delta h minus t delta s. So that means that this is also equal to delta h minus t delta s. Now let's pause for a second for some critical thinking here. We want ln k, delta h, we want r, we want delta s, and we want r here. Well, we have r, we have, sorry, and this is supposed to be rt. We also have t, we have ln k, we have delta h, here's t again, and we have a delta s. So it looks like we have all the components we want for the Van Hoff equation. Now we just need to be clever and find a way to manipulate this to be in standard form. Well, we know we want ln k on one side, so let's start with that. If we divide both sides by negative rt, we'll get this, ln k. So what we've done here is divide both sides by negative rt. We'll get ln k is equal to negative delta h over rt, the negative one up top, and then we're going to have minus, and this will be t delta s over rt. And of course t cancels out, and we have negative rt that we're dividing by, so the negative cancels, this becomes a positive. And so now we can just draw out the equation. I hope it's pretty clear that we're already in the Van Hoff form. ln k is equal to negative delta h over r, and I like to write it as times 1 over t, so I can see x and m clearly, plus b, which is delta s, sorry, we're working standard here, over r. This is the Van Hoff equation. This is what we expect. And you can see all the components are in the right place, and that's how you derive the Van Hoff equation. Now hopefully you have a kind of rudimentary understanding of graphs and algebra, and you can use that to pull out valuable terms from this equation if you're given a graph. And in my next video I'm going to go into how do you actually create a Van Hoff plot in Excel, which you're going to need for the homework, and I hope to see you there.